Okay, today we're going to look at a technology that you can do with DNA, now that we know how DNA functions and how it can mutate. Today we're going to look at RFLP, which stands for restriction, fragment, length, polymorphism. You never have to know that. Essentially what you need to understand is that what we're ultimately going to do is use this to do another process called gel electrophoresis, and you'll see it in the next slide. What you need to understand, though, is that restriction enzymes are capable of cutting your DNA at very specific sequences, and because everybody's DNA sequences are different just slightly, the way that your DNA cuts is specific to you. So because you have this unique pattern on your DNA molecule, you also have this unique pattern of cuts in your RFLP. Now, here's the thing. Here's what we do. You take a little microcentrifuge tube like this one, that's what this is, and you load it with this pipette with a sample of DNA and a sample of restriction enzymes, and you do what's called a digest, and the restriction enzymes will munch away at the DNA. They'll cut the DNA at the specific sequences, so you can kind of think of them like little chemical scissors. And then that's it. The RFLP is done. The problem is you'll notice that this little tube has a tiny little bottom right there, and the way that that looks when it's finished is like a little tiny slime ball in the bottom of this tiny little test tube, and so you can't really see the cuts. So to see the cuts from the RFLP, you have to do something. That something that we do is gel electrophoresis, and gel electrophoresis is going to separate the DNA fragments by size and charge. So this is going to separate according to the size and the charge. First of all, here's our DNA sample, right? And we've added restriction enzymes to it, so this is the first part. That's the RFLP where we've cut it. Next, what we do is put the DNA into a gel-like substance, and we're going to apply an electric charge to it. Okay, so we'll actually hook this up. There's like a little box, and it's kind of like a little battery, and there will be wires that will go to the gel. And so here's our positive here, here's our negative, and what happens is because the DNA has a slightly negative charge, it's going to run toward this positive electrode in that direction. Now, here's the thing. The smaller pieces are going to be able to move faster through the gel. The larger pieces are kind of going to get stuck in the gel, so the longer pieces are going to stay closer to the wells where you loaded the DNA. The smaller pieces are going to move a little farther down the gel. And ultimately what you're going to get out of this is a DNA fingerprint. You will get a unique pattern of DNA for each person, and this is called your band pattern. You can see the bands of DNA on these gels here. This is what a gel looks like in real life. This gel has had a fluorescent dye applied to it, so it kind of glows. But that's pretty much it. It's pretty much a simple process. It takes about 30 minutes of lab time to do. Really the thing that's the hardest is maybe getting the RFLP done first, and that might take another 30 minutes or so to let the enzyme digest, but really it doesn't take long to make one of these. Now this is particularly useful because you can do 3 different things with gel electrophoresis. The first of these is matching DNA at a crime scene. So if this was a crime scene gel and number 1 were some samples from a, say, it was a situation where a victim was murdered, and underneath the victim's fingernails you had some skin cells that didn't belong to that person. What you would do is try to see, is it suspect 2 or suspect 3 that matches this? And what you want to do is just look at each band and try to match them up, and you'll notice the suspect here that matches up is suspect 3. Suspect 3 has all of the bands in common with the samples that you see here. One last thing about this process. Oftentimes you're going to see running alongside of this something called a KB ladder. Okay, and this is lengths of known DNA. And the reason for this is because sometimes we're trying to get specific codes of DNA. And what we want is, say we know we have a gene that's 10,000 base pairs long. If I know that this fragment right here is 10,000 base pairs, and I know that this ran right next to it at the same time, I know that this must also be 10,000 base pairs. So this KB ladder can act like a scale so that you can measure the lengths of DNA, so that if you're trying to isolate one particular gene, you can do that. You can also see how long the code is if you are determining specific codes on the DNA molecule. The other place where you would use this is paternity testing. And paternity testing is the baby daddy testing. That's where you're trying to see who the potential father is of the baby, which one is actually the baby's father. And you're going to do one of these for practice. Last thing you need to know about gels and gel electrophoresis is that it's not uncommon to get a situation that you see right here. Now remember, if this is the top of the gel and this is the bottom of the gel down here, what a common mistake that students think is that these down here, these thick bands, are there because they must be really big. That's not the case. Remember, the smallest bands are going to be found at the bottom of the gel because the smallest pieces can move the furthest in the gel. What you're seeing in a situation where you get fat bands like this one down here, or this one right here, or this one right here, is that you might have several pieces running on top of each other. So you could have 2 or 3 or 4 pieces of DNA that are all the same length or really close to the same length running on top of each other. That's RFLP and gel electrophoresis, and now you guys are going to practice.